Imagine you're looking up at the Earth's night sky. It looks perfectly peaceful, right? But what you can't see is that right at this exact moment, there are literally thousands of invisible, silent machines whipping around right over your head. Satellites, spent rocket bodies, dead spacecraft, fragments from missions decades past. Most of them are totally invisible to the naked eye, but trust me, they are up there. Now imagine what happens when two of those silent machines cross paths at the exact same moment. That incredibly tense scenario leads us to the core question of today's documentary explainer. Could the ever-increasing number of satellites and orbital debris eventually make certain regions of near-Earth space significantly harder or even too dangerous to use? It's a concept that sounds like it's straight out of a science fiction thriller, but it's actually a very real operational consideration for modern spaceflight. To really grasp the magnitude of this threat, we have to start with something that seems super simple, but is actually quite mind-bending. So, let's dive into Section 1, the speed of orbit, and the physics of falling. Before we can understand what happens when things crash in space, we first need to clear something up. Why doesn't all this space junk just fall straight back down to Earth? I mean, gravity is constantly pulling on it, right? Well, an orbit is essentially just the act of falling. A satellite isn't peacefully floating in zero gravity above the planet, it is constantly in a state of free fall. But here's the catch. The satellite is also moving sideways. And it's moving sideways so insanely fast that as it falls downward, the curved surface of the Earth actually drops away beneath it. The result? The object keeps falling, but it just keeps missing the planet. And the sheer scale of that sideways speed is staggering. To achieve this continuous freefall in low Earth orbit, an object has to be traveling at roughly 7 to 8 kilometers per second. Let that sink in. Not per hour, per second. That is a massive number. Everything up there, every single functioning multi-million-dollar satellite and every piece of dead debris is traveling at these immense speeds, which creates a rather terrifying mini-mystery. What exactly happens when two objects both traveling at several kilometers per second actually hit each other? That brings us to Section 2, Anatomy of a Collision and Kinetic Energy in a Vacuum. A crash at these speeds is absolutely nothing like what we experience here on Earth. Think about a bad highway collision. Two cars hitting each other at 65 miles per hour is already incredibly dangerous. But an orbital collision, we're talking about objects slamming into each other at speeds measured in kilometers per second. At orbital velocity, this isn't just a crash anymore. It becomes a highly violent fragmentation event. Because kinetic energy depends so heavily on velocity, the energy released when two objects collide in orbit is it's absolutely enormous. So the crucial takeaway here is this. You don't need a massive Hollywood-style asteroid to trigger a disaster. Because of all that extreme kinetic energy, even a tiny, invisible paint flake, a rogue screw, or a small metal fragment can completely destroy a spacecraft at orbital speeds. And that brings up a really unsettling thought. If one tiny collision creates a bunch of new fragments, and those fragments are all moving at 8 kilometers per second, what happens next? Well, that takes us to Section 3, the Kessler Syndrome cascade, a self-sustaining threat. This is where a single microscopic collision escalates into a potentially massive systemic chain reaction. Humanity launched its very first satellites back in 1957. But by 1978, two NASA scientists named Donald Kessler and Burton Corpallet looked at the growing number of objects in space and proposed a frightening concept, the cascade. Fast forward to today, and we are dealing with rapidly increasing orbital traffic, making their 1978 warning more relevant than ever before. In theory, a cascade effect starts when the density of objects in a specific orbital region gets high enough. Then, bam, a single collision occurs, instantly producing hundreds or even thousands of high-speed fragments. Those fragments then spread out like a shotgun blast, dramatically increasing the probability of more impacts. Those secondary collisions create even more debris, which creates even more collision risk. It becomes a self-sustaining debris environment. Basically, an orbital junkyard that actively generates its own junk. Which leads us to Section 4, the altitude factor, and debunking the instant apocalypse. Now, before we start panicking, we really need to debunk this whole instant apocalypse idea. There's this huge scientific misunderstanding out there that one crash means the entire orbital environment suddenly becomes this impenetrable wall of death, permanently trapping us on Earth. That sensational idea just isn't how it works. Space is a complex, three-dimensional environment. It's not just a single crowded room. The risk of a cascade heavily depends on multiple variables. We're talking about things like orbital altitude, the density of objects, precise orbital inclinations, exact collision probabilities, and how long that debris actually stays up there. It's a highly nuanced equation, and altitude is perhaps the biggest factor of the whole shebang. Altitude helps explain exactly why some space junk is just a temporary problem, while other debris is literally a generational threat. At lower altitudes, the Earth's atmosphere is extremely thin, sure, but it is still present. This creates drag, which gradually robs the debris of its orbital energy, eventually causing it to fall and burn up in the atmosphere. So the debris lifetime is relatively short. But at high altitudes, atmospheric drag is much, much weaker. Objects and collision fragments can remain up there for years, decades, or honestly, much longer. This brings us into Section 5, Traffic and Dark Skies, the modern reality. Today, near-Earth space is getting incredibly crowded, and to prove this isn't just some abstract theoretical problem, just look at how the International Space Station operates. Because humans live on board, collision avoidance is totally paramount. Here is exactly how an ISS debris avoidance maneuver works. First, ground-based radar and optical telescopes actively track hazardous objects. Second, teams crunch the numbers and calculate potential close approaches. And third, if a threat is genuine, the space station actually fires its thrusters to physically alter its course and dodge the debris. It's a very real day-to-day operational reality. But we also have to balance this with the unbelievable value we get from space. Satellite mega-constellations provide immense benefits to society: faster communications, global internet connectivity, critical weather and disaster monitoring. Modern civilization literally depends on these. But the trade-offs are definitely real: increased orbital traffic, radio frequency interference, and bright satellite trails that completely disrupt astronomers who need dark skies to observe the universe. The debate isn't simply satellites are bad. It's all about how we balance space utilization with orbital sustainability. And that takes us to our final part, Section 6, Managing the Orbital Environment and the Cleanup Challenge. If we want to keep using space, we have to start treating it like a natural environment that requires active management. But we face this really fascinating engineering paradox. The solution to space debris must itself avoid creating more space debris. Now you might be thinking, hey, just send up a space garbage truck to collect the junk, right? But capturing an uncontrolled, tumbling object moving at 8 kilometers per second is unimaginably difficult. If a robotic cleanup system makes even a slight mistake and accidentally shatters its target, it could trigger the exact collision event you were trying to prevent. So, the absolutely crucial point here is that we have to be smart about this. The future doesn't have to be a disaster. We have really powerful mitigation strategies at our disposal right now. We can mandate responsible end-of-mission disposal so dead satellites deorbit themselves. We can improve our collision avoidance systems and our ground-based tracking networks so we don't lose sight of the small stuff. We can fund careful robotic debris removal research. And most importantly, we can establish strict international guidelines for sustainability. We still have time to keep our orbital highways safe, for sure, but it is going to require global cooperation. Which brings us to you. Humanity has turned near-Earth space into a place of enormous opportunity, but that opportunity obviously comes with responsibility. So I want to hear from you. If you could create one rule for every satellite operator in the world, what would it be? Tell us your rule and why in the comments, and subscribe to Curious Orbit for more space science.